So some of you have noticed that some of the electron configurations on the periodic table are a little unusual. And I wanted to take a quick look and show you why that is. So we're going to take, for example, the electron configuration for copper. So copper's electron configuration, according to the way that we've been doing it, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. That is the way it should look. If we look at the orbital filling diagram for the last couple of sublevels, the 4s2 and the 3d9, we don't really care about the rest of this. The rest of this will be just a noble gas configuration, but these two I'm going to be interested in. So here's what's going on with copper. 4s has 2 electrons in it, and the 3d, there's, remember, 5 orbitals. And there are 9 electrons to put into those 5 orbitals. So we go according to Hund's rule: 1, 2, 3, 4, 5, and then we go back 6, 7, 8, 9. This is the way it should look. The problem is this half empty, half full orbital. This 3d orbital is just 1 electron away from being full. And whenever you have a situation where you have a lot of orbitals in the same sublevel and it's almost completely full, it's a very unstable situation for this element. So what copper does is it takes one of its own 4s electrons and it promotes it up to the 3d. And so what we actually have then for copper is the 4s now will only have 1 arrow in there, and the 3d with its 5 orbitals will now be completely full. And this makes for a much more stable situation for copper. When you can fill a sublevel that has 5 degenerate orbitals, that's much better than having just one with 1 electron in there. So copper is actually going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. That's the actual configuration for copper. We can see the same thing with chromium, only slightly different. So chromium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4 is what chromium should be. And again, we have a situation where the 4s sublevel has 2 electrons, and the 3d, now this time the 3d, there are only 4 electrons in there, and according to Hund's rule, the 4 electrons have to be distributed 1 in each, like that. Well, we have a similar situation. We have this unoccupied orbital right here. And that makes for a very unstable situation. So chromium can do the same thing. It can promote one of its own electrons up there. And in so doing, 4s will now have 1 electron in there, and the 3d will have 1 electron in each of the 5 orbitals, making a half-full d sublevel. And that's much more stable than to have an empty orbital up in that 3d sublevel. So anytime you have a transition metal where you have a degenerate set like a D or an F, the P sublevels don't do this, just the Ds and Fs do this, that are almost full or almost half full, oftentimes that element will steal an electron or 2 from the previous S to stabilize itself. And so if you look through the transition metals, you'll find a lot of them that are like 4s1 or 5s1 and 3d5 or 3d10. You'll even find some that have no s electrons. They've taken both and brought them up to stabilize. It's an unusual situation, but it's one of the many things that the transition metals do that the rest of the elements don't do. So just a little FYI for you.